So, are there any questions so far? Okay, then if no questions yet, we can start and work on practical exercise task and see more complicated example how this is accordingly processed. And in the process, we will make a small Matlab program that will help us calculation of these weights. And basically, it will be almost ready program for Viterbi detector itself. However, not quite yet, but still it will be good enough for us to actually uh, get results. I have prepared already for myself this small, how to say it, template, yes, which I will be using to draw paths on. And well, you can draw on paper and make a photo and accordingly add this photo into your report, yes, that you can send. And or you can use any drawing software if you'd like to, but don't waste too much time on making smooth picture, yes, because it's more important to understand the process of operation here. And well, basically that's what's about this practical exercise is. So let's see first our tasks. First of all, we need to draw the state diagram for our channel. Yes, so this is basically this diagram for your specific impulse response. Impulse response for you is the same as for multiple practical exercises so far. It's again provided in this table. It's only thing it's not average, but it is simply impulse response, yes. And we are going to use the same impulse response as previous practical exercises again, yes. So that is the first task, to draw this state diagram. Yes, accordingly, you need to draw this diagram. It will be consisting of 4 states and accordingly 8 transitions, right? Next step is to encode your name, surname, 15 symbols. Yes, so for example, for me, I don't have in my name, surname 15 symbols, so I have repeated my name, so I get in total 15 symbols. I have actually already prepared for you your first 15 symbols and repeat it if needed for some of you. Yes, and you need to encode it into an RZ code format by using -1 symbol for consonant sounds, so sounds such as L, N, S, G, R, and so forth, and +1 for so-called vowel sounds, sounds like E, A, O, I, and so forth. Yes, so basically that's, again, we have already, I believe, in some practical exercises before done something, so you might search those previous practical exercise for help. I believe that was most probably here even. Yes. The only thing that previously we did so in inverse, yes, so vowels were -1 and consonants were +1. So now we need to reverse it, but well, it's not a really problem for you, I believe. Okay, so that's the second task, which is quite simple, yes, and we might as well already start writing our program, yes. So I'm going to make a new file and accordingly save it as practical exercise 6 to clear variables and input my signal. So and also impulse response, by the way, yes. So first of all, signals. Now let us denote these by, I don't know, for example, X as input, or rather than that, wait a minute, A. I believe it was A in our lectures, right? So these are symbols AK, right? And we are accordingly going to get YK as an output. So these are channel input symbols. Also, we need impulse response. Wait a minute. For me, I had it somewhere here. So my impulse response was like this in previous practical exercises. So I'm going to keep it the same. Impulse response of channel. So all of you will have 3 values, yes, so that will produce us in total 4 different states and 8 possible transitions. Yes, so that's how it's work. And also we will need eventually to add some noise with AVGN function and signal to noise ratio of 10 decibels. So we might as well specify this ratio here. Well, to noise ratio SNR is 10 decibels. So these are our input data for the program, and now we need to start thinking on how to make the first trellis diagram for this impulse response. We need this trellis diagram in the code as well. So we will write a simple program, and then I will use this paint here to actually draw this diagram. Well, we can actually in process. We'll draw this maybe in process as well. So I'm talking about connections. So actually, it's quite simple. I'm going to specify all the possible states. So need to generate a state flow diagram for specified channel. That is our task 1. And accordingly, for that, we need to specify some array in which I'm going to write down all the possible states and transitions, like +1, +1, +1, ending with -1, -1, -1. The first column is going to be AK, which differs, and the next 2 columns are going to be AK -1 and AK -2. Yes, so this +1 is AK -1, this +1 is AK -2. So there are a total 4 of such states, and accordingly, each state produces 2 of the transitions. Yes, so I'm going to simply specify them here, like this, +1, +1, +1. Next row is going to be the same state, +1, +1. Yes, so these last 2 symbols are the same as here. Yes, so basically I'm now working with this state, and for this state I can have input of +1 and input of -1. Then I go to the next state and also input +1, input -1. So the state is now going to be +1, -1. The input is +1 and the input is -1. Also, I use the semicolon to start a new row. Now I don't remember if this was really necessary. Okay, let me try without this and we'll see if we need to add it. Then the next state is going to be -1, +1. Again, the first symbol transmitted is +1, then the state, the transmitted symbol -1, then the state, and finally the last state, -1, -1, with transmitted symbol +1 and transmitted symbol -1. So here you can see these states. Yes, 4 states, 1 state, 2, 3, and 4. And here you can see transmitted symbol for each state. Now we can actually draw the connecting lines here in accordance with this state. Yes, so well, actually I'm going to maybe for now add these diagram here. I can have it nearby. Also, let us first of all try and see if this produces what we need. So this should produce a matrix that looks exactly the same way I have specified. So, okay, this copying didn't really work. For some reason, these symbols are not exactly minus, so be careful when you copy from PDF file into Matlab. It's different symbol. Sometimes not, sometimes it is. I believe it has different code for the symbol. And sometimes, Word, for example, can have autocomplete to replace this short dash with longer dash, and that is not really minus sign. So let's produce an error. Yes, we don't really need semicolons here to separate each row of the matrix. And here we have our diagram matrix. I'm going to suppress the output by ending it with a semicolon here so that I don't have it all the time in this command window. Okay, now we can draw these connecting lines. So I'm going to use different colors again. Yes, so first of all, let me process the cases when I have plus ones. So in this case, I'm going to transition into, well, different states. Yes, so let's start with this state. If I have started from this state and then I send +1, like this, +1, then the next state I'm going to get in is going to also be +1 and +1. So basically, I can say that the next state is going to be here, +1 and +1. Yes, so I'm going to use line of the, well, don't see these. Oh, okay, maybe these. Wait a minute. In lecture, we had for once red color. So let's be having this connection. Next one. When I go from state +1 -1, I'm going to end up into the state +1 +1, exactly the same way. Yes. So from this state to this transition, also +1. Then if I go from the state -1 +1, wait a minute, something is really, but no, I believe it is correct. Yes, it should be correct. So if I go from the state -1 +1, which is next state here, yes, with the symbol +1, I'm going to end up into this state. Yes, so this is going to be my new state where I go to. So in this case, I'm going to connect these lines. And finally, if I go from this state, -1 -1, and send symbol +1, I'm going to end up in the same state as here, yes, also. So you may observe that actually both of the incoming states are with the same sign. So here for this state, two states will be +1 and +1, and here also +1 and +1. Accordingly, these symbols will be -1 and -1, as you will now see. So next, negative symbols. So I'm going to send symbol -1 and end up from the state +1 +1 into the state -1 +1. Yes, exactly as I said. So now I'm going to, oh, sorry, I didn't really want to make that line blue one. It should be red. So to here. Next one is from state +1 -1 also to the same state. And it's not really difficult to understand where will go the next ones. This one will go here, and this one will go here. However, we still haven't calculated really the actual values. We only have plotted this diagram, which is correct, yes, but also, well, we need to calculate what value is actually being transmitted in the process. So for that, we need to calculate these values in our program. So I'm going to reduce this picture. Let's save it somehow, I don't know, on some desktop, like state diagram. Okay, so let's now calculate the actual values. Of course, you can do so manually by taking your impulse response. For example, let's calculate the first one. So transmitted symbol is +1. This is multiplied with the first impulse response value, which in my particular case is 1 and 2. Then I add next +1, which is this +1, multiplied with 0.7, and accordingly plus this one, multiplied with -0.5. So the value is going to be 1.4. And we can actually automate this process, and we still will need to input somehow these values into Matlab, so it's worth to try and calculate these manually. Yes, not manually, but automatically, I mean. So how do we do that? Well, it's not that difficult. Yes, we only need to find convolution between each row and this impulse response. So basically, this is none other than matrix multiplication. Consider that here we have first matrix, then we need to multiply with this matrix 1.2, 0.7, and -0.5. And once this multiplication is calculated, then we'll have a vector with 8 values. And the first value should be 1.4, which we have already so far calculated. Let's do this and see how it's working. Yes, so let's calculate according output values of state diagram. And actually, I'm going to update this matrix, replace it, and I'm going to multiply it with impulse response. However, my impulse response is a vector row, and well, I can actually make this a column in a simple way by specifying here semicolons or transpose. I'm going to use transpose at the end. And then now it's a column vector. Yes, so matrix with 3 columns is multiplied with the columns of 3 rows, which is correct dimensions for multiplication. So now I run the script, and I have these values ready. Yes. So what I need to do now is to correctly match them with one another. So actually I do want to see my original state diagram matrix to actually correctly match everything together. Yes, so now I need to write down all these values on top of these lines. Yes, so first of all, I'm going to reduce some font, make this normal script, red color. Let's first process cases when we transmit some symbols 1. So this one, 1.4, this one. Well, actually, let's take red one. So here and here and here. Yes, so accordingly, this is going to be 1.4. We can actually make larger font, maybe even bold. So the next one is going to be 2.4. Here then we have 0. And the last one is 1.0. Well, simply 1. Now for the minus signs, these are accordingly. For this state we will have this. For this state we will have 0. For this state we will have minus 2.4. And for this state we will have minus 1.4. Yes, okay, so here we have minus 1. I'm going to change the color. Here we'll have 0. Next one will be minus 2.4. The last one is minus 1.4. This is our state diagram, yes, of the channel, the task number 1. So I'm going to make this window smaller so that we can use it later on for our trellis diagram plotting. Yes. So, okay, we have found these states and we can now actually produce the output signal. The output signal can be calculated as a filtering procedure. So, channel output signal as filter result. Since our channel can be equivalent to replaced by a filter with this impulse response coefficients, then we can actually use command called filter to actually process our signal. These are our without noise, and we also need to add noise by using avgn function to our signal, and we have actually denoted this as Greek letter rho. Yes, and this resembles, well, Latin letter P, and accordingly I'm going to assume that this is our noisy signal rho. So we use avgn function with for signal y with signal to noise ratio SNR, and this will be with noise. So these were a little bit ahead of the tasks. So here we have display channel output in signal form trace diagram, which we still need to draw now. And also I have added the noise. And then we will need to draw detection process. So basically we then add, basically we can say that this is task 3 and this is task 4. Yes, so task 3. And here starts task 4. It's not only a thing that we need to do in task 4, but well, here, yes. The second task was just to write down this signal. So we can say that this is task 2, which you need to do manually, yes. So now we can run this program and produce the output. X undefined, of course, because I have marked my symbols as A, not X. And yes, here we have these results. Can we make it much short, for example, like this? Well, I don't really remember how we can reduce the accuracy of the output symbols, but it's okay. Yes, we can see our output signal that is being transmitted. And here are the noisy versions of this signal. Now, you may see here that we have transmitted symbol 1.2 and minus 0.5. And we didn't really have these options here at all. Yes, how did that happen to be? Well, this is happening because we assume that previous symbols were actually here 0 and 0. So for that, when we have impulse response 1.2, then we had minus 0.5, yes? Or what was that? 0.7 and minus 0.7 and minus 0.5. So in that case, the first value 1, which we transmit, is multiplied with 1.2, then 0 with 0.7, and 0 with minus 0.5. For this one, then we calculate, so minus 1 with 1 and 2, so minus 1.2, plus 1 with 0.7, and plus 0. Yes, so that gives us minus 0.5. And only starting with the third symbol, we can use all of them. Yes, so here we had to use some previous symbols, which we assume to be 0 in order to calculate this filter. Yes, but we will not really focus on that right now. We will start simply from k equal to 2. Yes, okay, so k equal 2. I don't need this anymore. I have this diagram, and now I need to basically write down what I have, what signal I need to send. I will maybe make it like this, and accordingly, I'm going to say that here I have k equal 2. So I'm skipping k equal to 1 and k equal to 0 because I don't have enough symbols to make correct diagram. I need to know what I'm going to start from. And in my particular case, previous symbol is going to be minus 1 and symbol before that plus 1. So I need to start from this state. Yes. And I'm going to send symbol plus 1. So from this state, I'm going to send symbol plus 1, and I'm going to end up into the state plus 1, minus 1. And in the process, I'm going to send value 0. Right? So next symbol I'm going to transmit is going to be minus 1. And from this state, yes, from second state, minus 1 goes to the state number 3. We can say that this is state number 1, state number 2, yes, state number 3, state number 4. So according to this plot, yes, we can see that the blue line goes to the number 3. So from each of these states, there goes out one red line and one blue line. However, only similar color lines are inputs for the next states, yes? So that's the structure of this trellis diagram. So we can see clearly that if we send minus 1, then we will go below here. That will transmit 0. The next symbol is also minus 1. We will go here. That transmits minus 2.4. The next symbol we transmit is also minus 1. That produces minus 1.4. Yes, and so forth. So the next symbol also minus 1. Again, minus 0.4. The next one is plus 1. So this should go to the second state, and it will accordingly produce the output of 1. Then minus 1. That goes to from the second to the third state and sends value 0. The next symbol is again -1. That goes to the state number 4, sends value -2.4. So then we have +1. +1 means that we go from the state number 4 with the red line, yes, into state number 2. So we spent initially a lot of time making this graph, yes, in order to simply know at once which line will be correct one, yes. So if we go +1, we take red line. If we go -1, we take blue line from the point we are starting from, yes. And in accordance, here we send value 1, yes. The next value is again -1, so we send 0. Then we have +1, which goes to the state number 2 and also sends 0, -1, and -1. So here 0, and here also -2.4. So this is our diagram for the transmitted signal. Yes, so basically channel output signal without noise. K = 3, K = 4, K = 5, 6, 7, 8, 9, and we go up to 12. No, 15, sorry, 15. We started from 2, so yes, we should end up with all symbols. 13, K = 14, K = 15, right? So 15 symbols have been processed, and this is the path in our trellis diagram for a channel transmitted signal without noise, yes? And if we compare with what we have obtained in Matlab or Octave, in that case, yes, you can see that this is actually the same, yes? So here we have 0, 0, -2.4, -1.4, 1.4, 1, 0, -2.4, and so forth. Yes, and the last value is -2.4 here. So we only don't have these values, yes, in this diagram, because we start from state which already contains this information, -1, +1, yes, in the relevant order. So I'm going to save this material to edit later for you to Ortus. Okay, so can I do so? Take a screenshot. Okay. Wait a minute. I need to actually mark this. Yes. And did it save? Just don't never use this option. Just don't want to, lose this. Copy to clipboard maybe, but it will be better to see it once. Let's start a new paint. Okay, so it's working. I'm going to save this as the channel output. And I will later add these pictures to Ortus for reference so that you don't have to scroll video and search for this. Okay, so this is our task number 3, and partially task number 4 adds the noise to this signal. As you can see, these values are now crippled. Now also you can see that because of this noise, we cannot really hope to consider the sign. it would work with these symbols to here, for example, say that this is -1, this is +1, but for 0, we don't know, is this -1 or +1 for certain. Yes, we cannot really decide that. And even slightest noise, yes, will actually set these off the balance, and accordingly noise will make this 0 either small plus number or small negative number, which will be random process and of course doesn't contain our data. And 0 can be either +1 and -1 if we so wait a minute, I do need to now find this diagram. No, that's not one. Okay, G files only. This one, state diagram. So as you can clearly see from this picture, there is either red 0 and blue 0. Red symbol is transmission of +1, blue 0 is transmission of -1. So it's completely undecided, yes? And well, we cannot really hope just to take into account the sign of the number in order to successfully detect, yes? Because in this case, it will be a problem. So we need to perform correct detection with Viterbi algorithm. And also you may notice that once you run this script multiple times, these noisy values will change. In order to avoid that, we can specify a so-called initial state of the random numbers generator. So if we read help on AVGN function, then we need to specify input signal, signal to noise ratio, power of our signal, and then so-called seed, that is initial value of random numbers generator. So we don't want to specify any power, so we are going to skip this parameter just to say that it's empty. And for the state, we can specify any number, for example, 0. Yes, so way, each time program runs, it will produce the same results. Yes, so I have run it once, 0.81, yes. Next one, 0.81, and so forth. So regardless of how many times I run it, this random noise will be, well, not so random, yes, because this is a so-called pseudo-random number generator, which works in accordance with some specific algorithm, and we can specify state in order to reproduce the same noise. Yes, and I would recommend you to do so in case you will need to rerun the script later, because otherwise you will have to draw a new diagram again. Yes, it will change completely. So, okay, now what we need to do is to actually detect this signal. And for that, let me remind you fast how this process is done. So we need to calculate all the possible weights, yes, between this diagram here, yes, so you can see here 8 possible values and each received symbol. So consider that, for example, we have received this symbol 0.81. Now we need to calculate all the metrics with these possible transitions. Luckily, we already have them in this state diagram matrix. Yes, so what we are going to do is to calculate this difference for first symbol, for example, and we also need to calculate the square root of, or the square of it, element by element, because this is a matrix. Yes. Now you can see these weight values. Yes. Accordingly, now what we need to do is to correctly assign them. However, I would recommend to spend a little time to make it more convenient representation, and then, well, we can actually work much faster. So my idea, which I offer to try for you as well, is to calculate the matrix of weights. So what I want to do is to describe this entire structure in some kind of matrix. Yes. So how can we do that? Well, there can be multiple approaches. First of all, we can write one matrix for red lines and one matrix for blue lines. And one matrix will contain new states, positions, and another matrix will contain these weight values. But this is a lot of different matrices and a lot of coding, and I have found, figured it out. I don't know, maybe this is a classic solution, but I tried to find out myself, and I offer you to make a so-called weight matrix. Yes. So basically, what I want to do is to actually store these values into positions, specific positions, right? So that I have a matrix of 4 by 4 elements. Yes, basically like this. And I want to store these numbers into specific places. Now, of course, I have only 8 numbers, and I will need to fill other elements with some numbers, yes, some different values that I don't want to use. But first of all, I need to decide in which of these cells I'm going to store my values. So, and the idea is quite simple. I'm going to store, yes, okay, wait a minute, state 5. Just a moment. I need to remember how I who did this. Yes, so state diagram 1. State diagram 2 minus 1 is going to be then the third. Okay, so now I think I have remembered. So I'm going to use the row number as the state number we are going from. Yes, so basically row number is here 1, 2, 3, and 4. As a column number, I'm going to use the number of state we are going to. Accordingly, here we have 1, 2, 3, and 4. Therefore, this transition will produce result here, and I write number 1.4 in this cell. Next transition in the first row will go from state diagram. State diagram 2, or no, wait a minute. From the second state. So, no, wait a minute. I think I have some problem. I need to check one additional material I have. To see if I did correctly this lot. So here I go from the second. Yes, so this is correct one. Yes, these are slightly different values, but this is correct. So this is correct. That is good. Now I need to find where I mistaken. So here we have 1.4, and here to second, that is from. Wait a minute, but this, okay, I understand. So this is 1.4. Then to this place we go 2.4. Everything is correct, exactly as I said. So here, accordingly, yes, because we don't have any, how to say it, any inputs from the first and second. So for the second, we go only from the third and from the fourth. So basically here, that would be also red colored ones. Yes, 0 and 1. Next ones will be negative, no, not negative, but basically remaining this. So for the state number 3, we go from state 1 and state 2, accordingly with values -1 and 0. And for the state 4, we go from state 3 and 4 with values -2.4 and value -1.4. So this way, the number of row is actually the initial state, and the number of column is the final state, yes? And the value itself is the accordingly what is being sent in the process, yes? Now we need to figure out what to include here. Considering the fact that we will find the minimum weight, we don't want to put zeros here. Actually, the good choice would be infinity, so that it will never be smaller than any of these values, yes? So now we need to write this matrix. We can, of course, do so weight matrix manually by simply inputting the values 1.4, 2.4, inf, then the next one, and so forth. But I would strictly advise against it and instead input correct values by referring state diagram values. So for my case, 1.4 is state diagram number 1, state diag 1, and the value 2.4 is state diagram value number 3, state diag 3. Then 0 is state diagram number 5. Yes, because we go with a step of 1. So basically 1.4, 2.4, 0, and 1. And accordingly, 1 is number 7. Yes. So that would be infinity, infinity. Well, we can actually make some tabulation here to align symbols. Yes. State diagram value number 5 and state diagram number 7. Like this. And then for the negative ones, this will be very similar. Instead, we will take even numbers, 2, 4, 6, and 8. Yes. So basically, I'm just going to copy this part. And here we have 2, 4, 6, and 8. Now this is our, how to say, the digital version of this picture that we can work with in algorithm. Yes. So here you can clearly see the same picture as here. Yes. So from the state number 1, we go to the state number 1. So this is 1 and 1. And the value is 1.4. From the state number 1, we go to the value, to the state number. We cannot go to the state number 2. We can go either to number 1 or to number 3. So we go here to the state number 3. And in process, we send value -1. So everything here is correct. This is our state diagram of weight matrix. Yes. And we are going to use it now to actually automate calculation of the weights. Yes. So we will need to calculate this weight. Yes, as you can see here, it will accumulate over the time. Yes, so basically here, here, and here, and we are going to end up with 4 weights. Yes, initially we need to set these weights equal to 0 because initial weight of each point was 0, and over time it changes. Yes, so now we will set these initial weights. Set initial weight values. So this is going to be zeros, and we need them formed as a column. Yes. Now we need to actually update this matrix. Update the matrix for each received symbol. So we need to make the for loop for some k parameter from 1 to number of total symbols, which we might add here, like n is length of a. So up to n. Side. The loop should be ended, yes, and here inside this loop we are going to update this weight in accordance with this matrix. So now, once we have these weights, we can find this difference in accordance with this Euclidean matrix. So this is our weight matrix. Yes, this is our raw k value. Now we need to find the difference and square it. It's not really difficult. Yes. So let's say this is going to be a weight matrix. Then we need not really y, but rho k minus this entire matrix, weight matrix, yes, and squared plus initial weights, yes. So we also need to consider that the first point should have some initial weights. For example, initially they are zeros, but over the process they will add up and we need always update it. So these are the weights I'm talking about here. Yes, for example, here it was 1, here it was 0, here it was 1, here it was 0. And we need to correctly take into account that it actually adds up and accumulates over the time. So we need to add these weights. Now, however, what we want to do is to add them correctly. So we should decide, should we add them as a row or as a column? Yes, here we have them generated as a column in order to output them easier. But however, here we should be very careful. So wait a minute, where did that picture go? I think I have closed it. Okay. Here it's again. So the initial point from which we are going is actually here. Wait a minute. So yes, from which we are going is 0 and 1. 0 and 1. Yes, we actually need this weight to be represented as a row, so that we add the corresponding rows. So weight of the first point should be added to here. Weight of the second point should be added to here. Weight of the third point should be added to here. Yes, third. And it needs to be, well, how to say it better? Okay, let's see it like this. So we are writing weights for these points. Yes, for example, 1 and 0. For example, 2 and 2. For example, 3, 4, and then 1 and 0. For example, like this. Yes. And we need to consider that we can get to this point for this weight we get from first position, and for this weight we get from the second position, right? We need to store them with these numbers, but we should add them accordingly to these numbers in the positions like here and here, 1 and 2, yes. But the, how to say it better? So this number now is the position of the final state, yes? So for the second state, we need to have the weights from the state number 1 and state number 1. Sorry, state number. Well, really difficult now to explain the logic behind this, but this will work correctly. If we add it as a column, it will not work. So we need this as a row, and currently I'm finding it difficult to explain my idea how I have came to this, but well, this is the solution how it works. Yes. Now what we need to do is to find the minimum weight in each of the columns, right? So basically, wait a minute, columns of the rows. Let's see. So if we calculate minimum, default, sorry. The default behavior of the program is to search the minimum per column, right? So in this column we found the minimum value -1, in this in this 0, in this -2.4, and in this -1.4. But now, since we have aligned our weights as a row, we'd like to search them minimum horizontally, right? So for that reason, we need to specify the dimension of the minimum search. In the similar way, we can read help for minimum function, and it says that in order to specify another dimension in which we want to search for this minimum, yes, we need to use this notation. Yes, okay, so we can say that we use empty brackets and then second dimension, because default dimension is the first one. Yes, this way now we have found the minimum in the row. And accordingly, this will be our updated weights, yes, which we will keep. So actually, as you have noticed, we will choose between two weights, either this weight or this weight, yes. This weight or this weight. Infinity wouldn't count because it's by default greater number than any of these two numbers. Yes, infinity is the maximum value I can input in Matlab, and it will ignore them basically when search for minimum. So this is exactly the same procedure we are doing here when we choose of these two weights which one is smaller. Yes, and now accordingly we can basically say that minimum is new weight, and basically that's it. We can add some printf line that will conclude this this k. Also we can say that, for example, printf, not fprintf, printf, that currently we are processing some value k equal to then this placeholder, the new line, and instead of the placeholder, we want to see the actual value of the k. And like this, so if we run this code now, it will produce us some problem. I didn't close the bracket here. Yes, okay. It will produce us with these calculations. Yes, so you can see here that we have calculated this matrix for the k equal 1 here, for the k equal here, and so forth. So actually, yes, so actually now we are going to use this to our advantage to actually plot the received signal. So for that, I'm going to need Matlab window here. I might minimize it. Okay. Oh, why doesn't it? I can resize it. And now I can move it. Okay. So here I want to see these weights. Here I want to see my states, original states. I can also maybe make it like this. This can be minimized. So now we want to start drawing. So the weights have been already calculated by this program for us. So how it works? Initially, the weights were 0 and 0 for each of these points. Now we can plot. Yes, so I'm going to choose some gray color, yes, to mark these possible transitions. So here is one possible transition, and here is another possible transition. For the first one, we have the weight 0.34. Please note that it's 10 minus 1 degree. And for the second one, we have transition 2.5. 2.51, maybe like this. Yes, obviously, of these two weights, the smaller one is this one. And accordingly, only this transition remains. Next one, for the second point, is 0.72 and 6.47. So for 0.72 for the first one, we have this up, yes, which is coming from the state number 3. Yes, we have here third column, so we go from the state 3. Here we have the fourth column, so we go from the state number 4. Yes, and obviously of these two values, this one is smaller. So this path is extinct. Yes. Again, next one comes from the 1 and comes from the 2, like this. Yes, and according metrics are 0.89 and 0.10. Yes, this one is smaller, so this path is removed. And finally, the last one so comes either from here or from here, which are 5.24 or 6.19. Yes, this one is smaller value, so only one path remains as the correct one. Now, for the first, there is also a mention in the practical exercise tasks that for the first sampling time interval, we need to provide detailed calculations of the weight for each transition. So this is the when we check if we have done everything correctly. So we can do so also by using Matlab. Yes, so let me turn on this, turn Matlab. And let's check this. So we have, basically we have all our values, real values here, defined in the state diag vector, like this. What we have received, the symbol, the first symbol, P1, is actually 0.81. Yes, and now we need to compare this 0.81 with each of these possible values. So we calculate P first minus state diagram, calculate the square. This way we have calculated. Oh, wait a minute, but I think I have. Yes, I do have some mistake here. Now, yes, here we had minus degree, and here we all even had even smaller. So yes, we will need to recalculate that. At any rate, the first ones should be calculated maybe accurately. Yes, so let's do the task. And then we will use this. So the idea is that first you calculate manually, then you check if everything is correct here. And then if it is correct, you can use the program to help you automate this process. So I have already showed you how to do that, but actually let me try make format compact maybe. Maybe this way it will produce better numbers. No, it still uses this notation. Format short G. Okay, now it's correct. Yes, so I needed to turn on format short G in order to avoid these exponents. So I would advise you to also turn on format short G. So now we need to calculate these correct values. So our received symbol, rho, first, is 0.81. So we calculate it like this, 0.81 minus 1.4 power of 2, which is equal to, accordingly, rho 1 minus state diag 1 square root, but the power of 2. Yes, so this is 0.34. Now, for the second point, we need to find the difference with 2.4. So that would be 0.81 minus 1.4, or 2.4, sorry, squared. That would produce this value. So that would be third state. Yes, state diag. It's 2.4 indeed. Yes. So, and the result is 2.51. Yes, 2.51. So the remaining 6 should be calculated in the same way. So here we calculate. I will choose different color. 0.81 minus for the second one 0. That would be accordingly 1 squared, 0.66. Well, roughly, yes, I'm making approximately. And here 0.81 minus 1 squared, yes, should produce, that would be, let's check, minus 5 should be 0.66 and minus 7 then should be 0.035, yes. So this is the closest point, plus 1, yes, to this actual value 0.81. Next would be 0.81 and 0.81 minus, so for this third, minus 1, that would produce plus 1, and minus 0, like this. This one has been already calculated, that is 0.66, yes, we had it here, and now we calculated it again, and this one needs to be calculated. So here I'm going to actually say that I'm going to calculate 2 and 4 at the same time, and accordingly I want it in vector form. Yes, so as you can see here, second one is indeed 0.66. That matches the transition from state number 4, right? No, it's not transition from state number 4. This is the fourth value from our this state diag matrix, yes, which is a diag for 0, yes, this blue 0. And this produces 3.28 roughly. I'm not rounding it correctly. Correctly, it would have been 3.29, yes, but I'm making it a little bit simpler. And you are also allowed to do so like this. And finally, the last ones, for example, blue color would be 0.81 minus 2.4, so plus 2.4 squared, and 0.81 plus 1.4 squared. Yes, accordingly, this would produce 6 and 8. Then you can always use well, calculator or calculate that manually, and this should produce the same value. So for example, let's check the 0.81 plus 2.4 squared. That's basically roughly the same, because, well, here it's not really 0.81. Yes, this is a little bit more. Yes, so we lose some precision here, but basically this is the same number. Yes, so that's a 10 332, and here we have 489. Now what we need to do is to choose the smaller value. So here smaller value is this one, and accordingly this path is maintained. For this one, smaller is this, yes, and accordingly the second path is maintained from the point 2. So this is this line, yes. Now here obviously this one is smaller, and accordingly that would be the second path, which is here. And finally, this one is smaller. That is this path, right? Like this. So if we now check our script operation, it should produce the same weights. So here you can see 0.34, 2.51. These are gray ones. So the magenta ones are 0.66 and 0.03. The green ones are 3.28 and 0.66. And finally, the blue ones are 10.32 and 4.89. Yes, so this is the calculations of, how to say it, well, basically detailed calculations of these weights that you need for the task 6 to provide in your report. So you can do that manually in a separate picture. Yes, because it occupied a lot of place here, and I will want to, well, make it simpler. Okay, so I'm going to again make the screenshot of this. So everything here will be taken care of, and then copy this. Now I'm going to open the paint. And save this as detailed weight. Again, I will also upload it to Ortus as additional material for you, as an example, yes, to be used. So now I'm going to erase everything that and simply write down these weights again so that it's easier and more compact. Yes, so basically that would be 0.34, which is smaller, and 2.51. And accordingly, this path remains. Next line is 0.66 and 0.03, which is this one smaller, which goes accordingly, according to this picture, yes, to the second, this from below, yes, here, then 3.28 and 0.66. This one is smaller, and again you can watch this plot to see which of them is. So here we have two of them. Oh, sorry, not this one, but these ones. Two of them, but we need to take the second one. Yes, so the real one would be this one. Alternatively, you can also check the number of the columns. So the column is the second, so we go from the second state. Yes, so I'm going to use this approach because that is the reason why I spent so much time figuring out how to make this matrix, so that I can watch simply column and then basically connect line. Okay, so the last point would be 10.32 and 4.89. We go from the state number 4 like this. Now the next part, we write next weights and plot these results. So accordingly, we now process this case. Yes, actually I'm going to scroll a little bit. The numbers will be marking the columns. Yes, and now I do the same operation again. So you need to provide detailed calculations only for the first step. Yes, now it will add up. Yes, and work as expected. So here we have 3.09 and 7.10. The most smaller value is here, and we go from this step to this step. Yes, like this. So for the second point, we have 0.72 and 6.47. So the smaller value is here, and we go from the second state. No, third state, sorry, from the third state, like this. Next state, 0.89, 0.10. This one is smaller, and we go from the second state. And finally, 5.24, 6.19. This is smaller, so we go from the state number 3, like this. Already you can see that these paths are somewhat, well, only this path is extinguished. All the others, one way or other way, are still possible, yes? Okay, let's go further. K equals 3. K equals 3. So the first point, 544. Now I'm going to write down only the smallest one, this one, yes, to save time. Accordingly, 544 is transition from the first point. Now, from these two, the smaller one is 11, 0.11. It is transition from the point number 3. So point number 3 goes here and produces the weight this. Next one, the smaller value is 0.74, and it is transition from the second state. So that's like this, 0.74. Now we'll speed up a little bit and basically be done with it very soon. So finally, here 524, which also goes from the third state, yes? Next, k equal 4. Here we have 5.13, which is transition from the second state. Next, 0.77, which is transition from the state number 3. Next one is 0.14, which is transition from state number 2, because we are in second column. And finally, 7.29, which is transition from the state number 3. Okay, we go further. So far, it never occurred that we have same weights, but it is possible to have same weights. For example, like here, I don't know, 21.5 and 21.5. Yes, so what do we do in this case? You are free to choose any you like. So for example, I will choose this one, so that will relieve this transition. In this case, algorithm can choose randomly. Yes, if it's some automatic process, so it doesn't really matter which you will choose. Most probably none of them will be continued anyway. Yes, so the choice is random and free if these weights for the same point are the same, which is also possible sometimes. Yes. So step number 5, yes, 18, 22, that is from the first. Next one is 2506, that is from third. Next one is 568, that is from the second. Next one is 017, that is from the third. So let's make few more. Now smallest one is 18.23, which comes from the state number 2. 5.14, which comes from the state number 4. 6.57, which comes from the state 2. And 0.20, which comes from the state number 4. Okay, let's continue. So 21.7 or 07, and this is coming from state number 2. 6.91. This comes from the state number 4. 7.67, which comes from the point number 2, sorry. And 0.24, that comes from the point number 4. Well, few more, and I will show you what we do next once you go to the end. I'm not going to finish it completely because, as you can see, the procedure is the same. So you repeat the same procedure over and over again. You choose minimum weight, you find the number of columns from which it goes. So that's the second one. You choose minimum weight 0.24. That goes from the fourth one. Then again, minimum weight 789, which goes from second column. And finally 593, which goes from this. Now, what here matters the most is that some of these paths are already extinguished. So once you finish this process up to the end, but wait a minute, do we have much left here? Well, it's quite a lot yet, yeah. I think we will stop here with this drawing. It can be continued, but we already draw enough to show you that actually now we can start reading some data. In order to do that, you need to actually mark the surviving paths. So surviving paths so far are these ones. Next, this one can be continued, and this one. Next, this one. And as you can clearly see, currently with this red, not really red, but magenta color, there is only one surviving path, like this. Yes? So we can read symbols here, 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 up to these points. Now, from this point, we are not really certain about symbols, but so far, up to this, we can read them. In order to read them, we need to compare them with these graphs. Yes? So here we can see that first symbol is red, which is 1. The next symbol is blue, which is -1. The next symbol again red, which is +1. The next two symbols are, well, not really even 2, but -1, -1, -1. And, well, we don't really know for certain yet, but if we would to judge from this weight, that should have been this. And furthermore, this. Yes? So this is potentially the one that will survive, yes. And if you would go further, this would also disappear, yes, and the only remaining path would be here, -1 and -1, like this. Was this our actual data? Let's see. So we need to see what was our actual data. This was +1, -1, +1, -1, -1, -1, -1, and we didn't get to +1 yet. So as you can see, this detection process is, well, quite, how to say, repeating, yes, the same operation over and over again. That's why this is some algorithm that computer has to do. Here, the task of this practical exercise was just to get a good hand on understanding how this algorithm actually makes this decision. And basically, the next lecture next week, which will also start at 9 o'clock, yes, next week, we are going to automate this process and try and send thousands of data symbols, yes, in order to see how this works and how many errors will be left after this equalization. So we've seen so far that for 10,000 symbols, we had like 5-10 errors with MSE equalizer. Will we be able to get this to 0? We'll see next week. So for this, I'm going to conclude this practical exercise, and well, you need to, wait a minute, actually, let us save. Let us also save these results. Yes, so that we can upload it to Ortus as well. Okay. Final diagram. So, are there any questions left? I realize that most probably you need some time to try and repeat that for yourself with your task. But if you will have any questions, you can always write me in email or maybe even here in Teams. If you need, we will be able even to, make some short meeting to answer your questions. So, okay then, if no questions, then thank you for your attention. Have a nice day and see you next week.